Hi, this is Elliot Fishman, and welcome to our latest vodcast. And this is going to be a multiple part look at cinematic rendering, looking at some of the basic principles, focusing on clinical applications, and speaking a bit about future directions. So let's get started. If you think about 3D imaging, it's really been around since the beginning of CT. There were early articles. Mike Veneer in the early 80s, so that's more than 40 years ago, spoke a little bit about 3D imaging. The first application was craniofacial. Remember, with slow scan times, the only thing you can do 3D on with any degree of accuracy might be bone. So bone, craniofacial, and then a little bit of skeletal applications. But the reality is what's changed over time, besides the fact that the CT scanners are so much better, is the fact that computers have changed. Remember, we started with a Pixar computer way back when. That was over $250,000 just for that computer. And it would take about 24 hours to do a single case of about 60 slices. Obviously, things have changed substantially since then. We also talk about how we've gone from hardware and hardware-based performance to algorithms that take advantage of specific hardware. We talk about how we've changed from basic hardware, big boxes, think Silicon Graphics, think Pixar, to small chips from NVIDIA. Things that were hundreds of thousands of dollars are now hundreds of dollars. The performance to cost thousands and thousands of times different. We talk about, because of new computers, the ability to have better user interfaces. You don't need to be a computer expert to be able to do a case. Obviously, the CT scan resolution and the speed of acquisition has allowed us to go from skeletal imaging to vascular imaging to cardiac imaging. If you can scan it, we can scan it fast, and we can do 3D imaging without any motion artifact. And then, of course, as we have increased clinical experience, as our referring docs, whether it's surgery, whether it's GI surgery, whether it's orthopedic surgery, whether it's neurosurgery, and our fellow friends in medicine, whether it's in GI or it's endocrine, their needs and understandings of what 3D can do also drive us on a daily basis. Now, if you look at our experience, I mentioned way back when we had actually PD-11s that was using digital equipment on the original scanners. Then our first freestanding system was Pixar, which needed a Sun workstation as an interface. In the late 80s and 90s, Silicon Graphics became the big dog. They had expensive hardware. Their boxes were $150,000, large, needed special power, but they had lots of speed, and they were the state of the art until you saw chips come along, whether it's NVIDIA or whether it's Dell, making cheaper boxes with chips on board. Everything changed. And this migration from dedicated hardware to special purpose boards and GPUs really was one of the biggest changes, and why the costs came down to the point that before only a few people had 3D capabilities to now, whether they use it or not, I don't know, but every scanner has 3D software. One of the things that happens as your computers get faster and you have more experience in development of software, your algorithms change. In the beginning, everything was shaded surface. We don't use that at all anymore. Things were 0 or 1. It was all binary, black or white, which was okay for bone, but you couldn't see soft tissue. MIP came along. It was sort of a step forward. It would show the brightest structures, so it could work reasonably well for vascular structures, particularly if you remove bone. And then in the mid-1980s, Pixar came along with volume rendering. Remember that RGB, you could look at any tissue type. Things weren't zeros and ones. You could have partial pixels with soft tissue and bone or soft tissue and air. And then, of course, what we're going to focus on today, it's what's come about most recently over the last 5 to 7 years, cinematic rendering, which is a form of volume rendering, but it takes advantage of the very fast chip speed and capabilities to really do a lot more than we ever could do before. So if you speak about CT data sets, and I'll just talk about that briefly, the ability to get sub-millimeter slice thickness routinely at intervals that are sub-millimeter, higher spatial resolution, fast acquisitions which allow us to expand our capabilities, particularly in the vascular realm, but also not to have to worry about patient motion. Things like dual energy CT for acquisition, for display, for things like bone removal, and of course perfusion CT, which also will be very important. As we go forward, the newest thing in CT is photon counting CT, and that should provide better images for us, but more tissue characterization, which could lead to all sorts of new applications. But we'll see what happens there. Now, I mentioned that increased clinical experience drives demand, the need for increased diagnostic accuracy, the need for the ability to use imaging for preoperative planning, the improved communication between radiologists and referring physician is one of the things that 3D provides. And with the increased use of laparoscopic surgery and robotic surgery, the field of view for the surgeon is a lot different than just opening the abdomen. So they need to know a lot more in advance. And so this will provide that. And also, we talk about with the ACR, value over volume. It's not how many cases you do, though probably your administrators want you to do as many as possible, but it's value over volume. Not only do you need to do volume, but you need to do value. What you're doing needs to impact patient care. State of the art, 1980. Okay, that's the head, that's the mandible. This was shaded surface, thick sections, 10 millimeters thick, every 10 millimeters. But it was a start. These took hours and hours to make these images. Yes, you can actually see the spine. By 82, we did a few images like this. This is dysplastic hip. But again, shaded surface display, thick sections, binary classification. Everything is black and white. But it was a step toward 3D. And then, of course, 1985, Ed Catmull, who was the head of Lucasfilm's computer division, then eventually became the head of Pixar, became the head of Disney Studios. Ed retired a couple years ago, but now is doing other great things. When they showed this at RSNA in 1985, you were able to see the images rotate. This patient, you could see the white, the red, and the green, which meant you could see soft tissue, muscle, and bone, which was impossible to this point. And so the thought was that this was really the birth of volume rendering, which it was. Pixar had the patent on volume rendering. It was an article published by Bob Drebin, Lauren Carpenter, and Pat Hanrahan a couple years later. And these were the first images that were generated. These images spun. There was 82 images generated, and it rotated. And at RSNA, when it was shown in the Philips booth at that time, people gave it a standing ovation. I've never seen people applaud for technology at RSNA. I don't care what the technology was, but for this, people did. Now, lots of articles in the beginning. This was a good article by Gershon, and he was at MITRE. Visualization is the process of transforming information into a visual form, enabling users to observe the information. The resulting visual display enables the scientist or engineer to perceive visually features which are hidden in the data, but nevertheless are needed for data exploration and analysis. And perhaps in my mind, this article was so important because it took you away from 3D, the term 3D, whatever 3D meant, into more visualization. So everything we've spent our time doing ever since then is really visualization. Can we understand the data sets better? Now, I have to admit, my understanding or my thoughts of what was going to happen in terms of 3D has been a little bit off. This was a state-of-the-art article published in Radiology more than 30 years ago. And I said that as radiology entered the 1990s, we predicted that 3D imaging would be everywhere, anywhere, all the time. I was wrong, and I published an article in 2006. And look at that statement. Within a few years, 3D imaging will no longer be a specialized study done on select patients, but will also be part of a review of routine cases as well. That's only 17 years ago, and I was still not exactly right. And this article from 2012, post-processing of CT data is thus no longer an option, but a true requirement in this era of 64-row multi-detector CT and beyond. Again, More people are using it perhaps in select cases, but it still hasn't really had the impact I thought it was going to have. Now here's the article about volume rendering. Bob Drebin, who became the lead chip designer later on at Apple, Bob and Lauren Carpenter, who's still at Pixar, Pat Hanrahan, who's still professor at Stanford. All of them are doing incredible things. But this was that incredible article using medical imaging, showing you what volume rendering could do, creating those final images. We got better over time. Derek Nye did a lot of work with me, and he was able to make those Pixar computers hum. We could get down to about an hour reconstruction, and here you can see the soft tissue and bone in this right acetabular fracture. Look at the detail of the information. Again, not bad when you consider this was 4 millimeter thick sections every 3 millimeters. We were not yet to the era of isotropic data. And again, here was our first article. Volume rendering differs from surface rendering in that all of the information from the CT scans is preserved, not just surface boundaries. Object thickness and internal contours can be seen in the 3D projection. And that really was everything. Volume rendering, even today, is a percentage classification technique, so is cinematic rendering. Volume rendering assumes that a voxel can contain more than one tissue type, and the amount of each tissue type is between 0 and 100%. And so each voxel is therefore accurately represented. Before volume rendering, this was not the case. The technique is implemented using a probabilistic classification involving a trapezoidal approximation. Each tissue type is assigned a nominal value range that represents that tissue type. Each voxel is assigned a color and transparency by taking a weighted sum of the percentage of each tissue present in the voxel, and trapezoids can be adjusted in real time. When you think about it, this has been a 30-year journey. As computers get better, as chips get better, as rendering gets better, all of these things constantly are the same, but are improving what we can do. And of course, the final images produced by casting simulated rays of light through the volume containing the classified and colored voxels, and then the image is projected on the computer screen. Cinematic rendering, as we speak about it, what that does is instead of a single ray of light, has infinite rays of light, which increase the shadowing, which help increase the quality of the images. Now here's volume rendering at its best. You could do grayscale or color, nicely looking at the tendons, making things more opaque or less opaque. More opaque, you see the skin and the vessels, or even hiding the vessels and just showing the skin and the toenails perhaps. Or making it more transparent, where you hide the skin, you hide the muscle, and you get down to the tendons and to the bone. The techniques of MIP and volume rendering, I'll cover them a little bit, but I think the biggest issue, and it's still the same, remember MIP imaging I do like for looking at the liver, and I do like for looking at vessels, and I use it with volume rendering and cinematic rendering, but it's a projection technique, and what happens is it just projects the brightest structures. It does not take into account where things are in the volume. With volumetric rendering and cinematic rendering, things that are closer look closer, things that are further look further. With MIP, whatever is brightest is closest to you. So something could be in the back of the image, but if it's very bright, it seems like it's in the front. So potentially you can make significant mistakes if you're trying to use MIP as a way of localizing things, because it's going to be wrong. And this is a chart from an article we wrote which explains it very nicely. And here's MIP versus VRT. You can see there's some a form, a skeleton inside this mass of this house, basically. You can see with the MIP, you have three structures all kind of overlapping. With the volume rendering, they're separate, and the relationship matches the original data. Again, volume rendering and cinematic rendering prioritize where things are in space. And so when you're doing 3D, it's much easier to understand and be correct when using that information. The more complex the structure, here you can see 4 poles and 2 cross poles. The more complicated the situation, the more volume rendering has advantages over MIP. And again, this illustrates it very nicely. Things we need to do within the data set, we often will remove structures. There's a lot of tools for editing. We can do vascular editing and bone editing using dual energy. That works very nicely when you want vascular maps. For structures, you're able to remove things like the femur to be able to look into the acetabulum. There's different tools for doing that. You can remove the iliac crest and simply isolate the femur by itself. So depending on the situation, we may need to isolate structures. So editing tools become very important to us. And you can see very nicely in this case, where if you were looking at the MIP images, the femur would obscure the femoral arteries. But if you take the bone away, you can see the entire vascular map of the common and external iliac arteries and femoral arteries as well. And again, with volume rendering, that's not going to be the problem because, again, with volume rendering, relationships of structures are correct. The artery sits above the bone. Nevertheless, you still will often want to remove the bone to get better detail of the vascular structures. And at times, you'll want to remove the vessels to get a better look at the bone. And you can do both of those very quickly in practice. Now, with cinematic rendering, let's look at some of the basic things. And I'm just going to start off, and then we'll come back with part 2 a little bit after. So things we're going to look at are principles, implementation, clinical applications, future directions, and potential applications beyond simply visualization. Now, if you have to give credit, you always need to make certain that you thank people who've done some of the critical initial work. We mentioned Bob Drebin, Lauren Carpenter, and Pat Hanrahan for volume rendering, but Croes from the Netherlands is the one who really came up with cinematic rendering as a way of seeing if the faster NVIDIA chips can improve on classic volume rendering. You can see from his article the multiple light sources, the shadowing, the ability to create with raycasting and filtering and a Monte Carlo integration, the ability to create high quality, high resolution images. And what happens, of course, you can see in this example, with cinematic rendering, one of the things we can do, like with volume rendering, but do it more interactive, is basically change the rendering technique on the fly. So you go from skin to muscle to seeing enlarged inguinal nodes in this patient with a history of IV drug abuse. You can see the bony structures, the vascular structures in the left groin and lesser in the right groin. You can see broken needle fragments. But again, we can do this interactively. So the ability to use cinematic rendering when done correctly, I won't say it's a virtual autopsy, but it's virtual analysis of all of the patient's soft tissues and bone and any pathology present. And again, just think about that. Imagine if you were reading every CT like that. The question is, can we develop tools that allow us to look at the volume of CT and in real time be able to do this? Now, we can do it now, and we do it, but the question I always had is, can we integrate that into practice so it's a standard of care about how we look at information? That's not quite there yet, and it may take some time, but it's definitely doable. In the article by Croes, in addition to the fact that photorealistic volume renderings tend to be aesthetically more pleasing, it's been shown that realistic lighting contributes to 3D understanding and can improve depth-related task performance. With this work and the implementation that we have made available, we hope to contribute to the uptake of realistic illumination in interactive direct volume rendering applications. And that's just a wonderful article. And that article was written just only a few years ago. The initial articles using this in practice, this was in Insights in Imaging. As a result, the physically based volume rendering method called cinematic rendering computes in real time the complex physics of lighting effects. It models shadows, ambient occlusion, multi-scattering, and color transmittance, as well as sophisticated camera properties. So again, this approach leads to a natural and physically accurate presentation of the medical data with a focus on enhanced depth and shape perception. Again, everything to us is accuracy. And we personally got involved, and here's an article in 2017, very early, talking about cinematic rendering and its photorealistic image quality. We spoke about how we can create these 3D imaging with thousands of light rays traced to compute the resulting image. We spoke about how the lighting model with cinematic rendering and both classic volume rendering are based when reconstructing the image accounts for the difference between the two techniques. It's all the lighting model. And again, inversely, cinematic rendering assumes the global illumination model, which accounts for the impact that all light rays have on image reproduction. Again, these multiple light sources are one of the key concepts hiding within cinematic rendering. Now, there are limitations, of course. While photorealism improves the image quality and allows for better perception of structures, it's possible to have scenarios when too much photorealism is bad. For example, if some tissue parts are obstructed from the light source, the tissue becomes darker, which can be very realistic but omit critical information. One of the things we realize, even going forward 6 years, is that with cinematic rendering, I could show things that are hidden in the data set, like a small pancreatic cancer, but if I don't render correctly, I can hide things that are in the data set. One of the things we look to the future is AI, where AI will pick the absolute perfect rendering for us, not hiding things, not obscuring things, but making everything important show up, but not creating pseudo lesions. And that's going to take a lot of work. So let's talk about image creation. But I think I've used up my time for part 1 of this talk. Let's come back in a few minutes and let's do part 2. And I'll see you then. If you like this video, make sure to subscribe to the CTisus YouTube channel. You can also visit us at ctisus.com for even more videos, plus quizzes, pearls, protocols, and oh so much more. We're also in the App Store and have well over a dozen apps for iPhone and iPad, all completely free. Thanks for watching.